page that I think it's probably been mostly cleared up, but it's looked as if you were always correlating the thing on the left side.
I was.
Or the one with number 1 or whatever.
I was.
As if maybe you can't correlate the one on the right-hand side. It would be better to kind of randomly jump around and say, well, let's say we push it.
No, well, if I randomly jump around, I see, yes, okay.
And then we've got 2 well correlated this time, and some other time randomly choose number 3.
No, just a moment. No, just a moment. Let me just say something and see whether there's a misunderstanding in reality or just in words, okay? What's possible is to make copies by a certain process, which I can call, for instance, one of the processes of making copies would be, the hell with it. Don't pay much attention to what's in the other, and all correlations are lost. What's in one box has nothing to do with the other. That's a lousy way of making copies. One of the best ways of making copies with the most amount of correlation is there is a special way, I mean a special kind of interaction that you have to make these copies. It's a process, the printing process, whatever, which makes the copies a special way so that what happens with the left button is correlated perfectly. That I can push any one of these boxes and it'll agree, but only for the left button.
But you can make it so that...
However, there's another process by which I can make another 1,000 sets of boxes. But I have to have the interactions different. I have to know what I'm doing ahead of time. So I make the copies. The process of making the copies is different. And for that one, it's the central button, which is correlated for all the boxes. And this third way of making the copies, the correlations, could make the third one agree. And there are other ways of making the things so the correlations aren't perfect and so on. But the more perfect ones are the more interesting ones. Is that what you want? I can do one or the other or another, and I can make... We can discuss other possibilities, but I wanted to clear up this. Does that clear up this difficulty?
Could you say instead of left button, any specific button?
Yes, I could choose any specific button, but I can't choose the button after I've made the correlations. The process for correlating it depends on what button I'm aiming to correlate. Okay, I got to know that ahead of time. There's a left correlating measurement scheme.
In other words, you can't take a population where number 1 correlates and mix it with a population where number 2 correlates, and then do an experiment to find out which is which.
Well, I don't know. I have to think about that. If I mixed them up and then I tried to check which were in pairs, I might be able to figure out which is which. I don't know. Yes?
Do you mean that you don't mean, like in our problem, it's not the initial button, but a specific location?
Yes, left, right, and center. We've been using that one.
So we can only choose one of those locations, but it's not the initial press that we
No,
like.
no.
Because in our example before, it was the initial press, no matter which position it was.
That's correct. That's right. Yes, 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 yes. I see now what was... Good, good. Now we get the problem. Yes, yes. Last time it was the initial press that was correlated. But if this is correlated on the left, you remember, however, that although it was the initial press that was correlated, it's still true that if you don't push any other button, they're still correlated. You can measure either one again and again and again. They always agree, right? It's just that pressing some other button screws it. Right. Now, with this setup, you can push this button on any one, and it'll tell you what it'll get for any other one. And you can push it again and again, and if you want, okay? If you pushed another button over here and found out what that was, you could still find out what this used to be by pushing one of these boxes that hasn't been touched before, or has. Depends on how it's been touched.
So those boxes are all loaded that in one particular position, there is a constant, so to speak.
That's right. In one position left, there's a complete and perfect constant agreement, but not if you change, not if you... Well.
Can you change the correlation in a given box setup to say from number 1 to number 3?
No, you've set it up.
You set up initially with 1.
Yeah.
And now I'm manipulating buttons.
No, yes and no. I'll tell you how you have to do. Okay, he wants to do something. We'll come to a lot of things. We'll have fun discussing this. We'll take a time out. It's nothing. We've already understood everything, but this is just to tell you, attempts to beat the game by making copies doesn't work. And this is what but you can do something with copies. Okay, his idea was, we've got the left ones copied. Can I do something to this box so it gets correlated to the right end? Not by touching just this box. I can by taking a whole bunch of boxes into my room and doing something with them, turn the whole system into the other kind. But I can't do it if I only got a few of the boxes. I have to have all the boxes. You say, yeah, but I'm only interested. Can't you just make these few correlated? No, because I haven't got the other boxes. I can't turn these, I have to have the entire population to turn any of them so they're correlated any other way, okay? I can only disconnect the correlations by touching a few. I touch a few, I can screw them up, of course. In fact, an easy way to screw up the correlation of this is to measure that. We know it changes the odds on that one. But if you say, oh, hell, so I screwed this box up, so I'll throw it away. I still know what number one is going. Just use another box to measure it.
Could you at some point say how you actually prepared this?
I probably will. It gets a little technical, and I don't know. I haven't prepared that. I'll have to think of a way of describing it in a simple way, a precise example of such measurements.
Right.
Yeah.
That's what I'm waiting for.
In the EPR,
You might have to wait longer than I think.
thought
Yeah.
experiment, when you talk in terms
Just two of them.
Okay, but we talk in terms of if you measure, if they're identical, even in opposite directions using mirror image to
Right,
make it
right,
the same
right.
and so forth. What was that assumption based on, though? That you could in fact produce identical, so that you could measure one aspect of
It
one?
was based on the equations that of the quantum mechanics that had been developed at that time. The Schrödinger equations would tell you what would be the result of various kinds of experiments. And they're still the same equations today. And so they would use those equations, and he explained how those equations would produce this effect.
Could you in nature produce
Yes,
two particles?
yes,
That one where you could measure
Yes.
momentum and one?
yes.
How do you know? Okay, all right. I have to think about how one knows that they're in fact identical, other than saying they are identical.
Well, we don't know whether the particles don't have to be identical. All there is need is that one measurement predicts the other one. Sorry, complication.
Well, I'm identical in the sense that either.
What I mean by
either
ident- what he's
position or
worried
position
about-
is identical.
Yes, that's okay. Well, that's because the mathematics predicts it, then you check it and it works. What he meant by the identical, this box doesn't have to look exactly the same as that box. I can make the same thing with a blue box here and a green, bad using those colors, a blue box here and a purple box there, or a square box here and a round triangular box there. The particles don't have to be the same. The objects that I use to load them don't have to be identical, but they have to have three states so that I can make this measurement and charge the boxes, but I could be charged with this correlations that we've been talking about previously or now. So the identity of the boxes is not an essential feature at all. Okay, the identity of the results is what counts in this discussion. So because of this, it means that we can do what we call measuring what this button would give, which consists of making this kind of special left-hand copying system and sending you one of these boxes, or two or four. You want to know the answer to? I'll send you another group of boxes, 3 or 4 boxes if you want. And if you want to know the answer, I'll send you another 3 or 4 because I made thousands of them.
These are microcircuits.
Could they be used underwater?
Yes, anyone can be carried underwater and done anything you want it with it, and it'll work. Of course, you got to be careful. There's no leak or the water gets inside. I mean, it's possible to screw it up, but if you protect it, it's okay. But it doesn't be any distance.
Are you in the business of manufacturing these boxes?
In general, we are. That's called measuring. Because what we do when we measure is just say we have an atom, and we do something with it, and then we're able to publish what the result was for its spin or for something else. In this case, what would happen if we push button 1?
Can I order 10 boxes?
Yes, not this particular.
Can dolphins press your box?
Certainly. Yes.
Their rostrum?
Yes, dolphins can press the box. Computers can be designed with random number generators to decide which one of these buttons is pushed and record all the results and so forth. And so it doesn't require mankind to do it. You say, but sooner or later the man has to look at the notebook. True, because otherwise we aren't going to know. You can't be us who know unless we look, right? So therefore man is essential to all observation. Yes, for all observation that he wants to know about. A perfectly understandable philosophical principle with no depth, but great profundity.
see you and a dolphin facing up to one another.
Well, that would be fun, yes.
We can arrange it.
Having fun.
They have connections.
Yes,
In this last example,
Yes.
you're telling us now that one of the positions is perfectly correlated.
right.
And the rest of the story is that then in the other positions, you'll get a 3/4, 1/4.
Yes,
kind of
yeah,
distribution.
they're not correlated. I push one here, I might get green. Another one, however, will not necessarily agree. It might be red. If I made lots of boxes and just measured all of these central buttons, I'll get greens and reds, either 1/4, 3/4, or 3/4, 1/4, or something else. It may be as sloppy connections, but let's say 3/4, 1/4, or 1/4, 3/4. And from which way it is, I can determine what I would have got from one. In other words, if it's 3/4 green and 1/4 red, I can conclude that that means that this was probably correlated, that one's red. See, knowing that these are correlated, suppose we know how we made them, so we know they're correlated. Then we know that all these buttons are going to agree one way or the other, either reds or greens, and I can determine which one it's going to be by checking the second button only and finding out whether it's a predominantly green or predominantly red, 3-to-1. If it ain't 3-to-1, I'm screwed. Something went wrong with the experiment. It'll always be 3-to-1 one way or the other. And when you measure with enough of them until you're convinced it's about 3-to-1, more for the green than for the red, you know why I say you have to measure a large number, a reasonable number, because accidents can happen. Then, after you've determined it's 3/4 green, you can predict what will happen if you push red, not on the same box that you've used, because you know, when you measure that one, you screw up this one, so it isn't going to help any. This one's then 3/4 the other way. However, a box that you haven't touched yet, you haven't used yet, in order to get the statistics on the central button, if you push the left button on that box, it'll be red. Not on the box that you played with already, because in those boxes that you played with already, they're the universal rule. They're all independent then, you see, that if this is green, the chance of that one being red is again 3/4. Yes. And if this is red, then the chance of that being red is only 1/4.
I thought they were all perfectly correlated.
They are.
First.
They are.
So what information does that really give us?
That the only information it gives us is that we know what we would get for any box by looking at any other box for left pushing.
It allows us to separate them without.
Yes, so that you can publish what you observed, you say, about the first box, the early box.
You sink your assumption back in.
Yes, yes.
What happens if you have three?
That's right. And what happens in nature, on a large scale, if there's anything, it's always this kind of correlations, that at least that are interesting, unless it's just chaotic. So all of the physical world which we analyzed before, where we found laws and so forth at a large scale, we're always in situations where we had millions of these things correlated, and therefore the reality looked like it meant something to say that that was red or that was green or that, because we could check it all the time by looking at any other place. So it looked real. It only looks real because we have so many copies. But what we've discovered is that we can't make copies of more than one thing at a time, which is another way of saying making copies is a measurement, we could say, in a way. So we can't make copies of two that are correlated on two different lines is a statement. We can't make measurement of the two different quantities simultaneously. That's the uncertainty principle. Okay? I just want to compare making a measurement with these copies. You say, what has that got to do with it? What's the matter with pushing this button and looking at the light? Pushing the button and looking at the light really was making copies. Because a light, a real physical large bulb, puts photons out in all directions. You looking at the bulb can see it's red, and I'm standing over here, I can also see it's red, he can see it's red, he can see it's red, everybody can see it's red. That's an example of the correlation. It doesn't make any difference which box you look at, which photons, over there, or over there, or over there, they're always the same. That's this kind of correlation. So what we used to talk about crudely as pushing a button and looking at a bulb was really a mechanism for making this type of correlated copy. Okay? That's the same thing. And the laws of interaction of matter permit us to make such copies, but do not permit us to make copies by which we can determine make a correlation that works both for the first button and the second button perfectly. We can make it perfect for the first button, but only 3/4 perfect for the second button. Now, mind you, there is a correlation in the second button. It just isn't perfect. The first button is all agree, but the second button, they don't all agree, but 3/4 of it, it's more likely to agree than not. Okay? That's what I meant. It's more likely to agree with each other than not. Yeah, I said it right.
Just a beautiful model for me.
Yeah, it's getting better, right? Good, we're getting somewhere.
Now, if you had an observer that had a very peculiar visual system in which, when it showed red, he would sometimes see green.
Yes? Okay. Oh, sometimes. But then, let's say I have a... Oh, then this fella wouldn't be so hot at making observations of the world. He would be drunk most of the time.
No, but then he would...
I mean, it's like asking for a drunk observer. He doesn't make...
No, then he would correspond to box number 2.
Oh, so he fit in.
He would make number 1 into a number 2.
But he'd make number 2 into something totally different.
He couldn't observe number 2 because his 3/4 probability.
Exactly.
And you wind up with a, you don't.
Yeah, whenever he observed, he's not very well correlated with...
Right.
He's only partly correlated. Yes. There are observers like that, yes.
Yes, there are.
In fact, in certain...
Especially when they have LSD in.
Yes, but also in a certain sense, we are observers like that because we can only amplify certain aspects of small things. This is an example. And so we are sort of seeing crudely, right? Right. Seeing crudely. And so one way of looking at the uncertainty in the world is to try to suppose that that these things are there, but we only see them crudely. This idea we have to get rid of. It doesn't work. Because the whole discussion of this pair of boxes was this idea that there are red, green, and green, or green, red, red already, but we can't make it out very well. When we push buttons, it changes, it screws up. And that doesn't work, that's not enough. The world is still worse. We can't really understand the quantum mechanics by saying, there are all these things. It's either one, that's red, green, and green, or whatever combination. We just don't know what it is. And look, we don't see too well. That doesn't quite work because of this business of correlating these boxes as demonstrated, or the Einstein-Podolsky-Rosen paradox demonstrates. So the early ideas, if anybody first had them, that there were these things like position and momentum, but you couldn't just quite make them out simultaneously. It's not enough to understand the character of quantum mechanics. You can't say that there's both a position and a momentum simultaneously and be logically consistent in your predictions after that, after you've made that assumption, and use normal logic with what we observe. So we have learned not to say things like a particle has to have a position, have some position, I don't know what it is, but some position and momentum at the same time. That statement starts out by making an assumption, which sounds perfectly reasonable, because I can measure the position, or I can measure the momentum, but I can't measure both at the same time. But to suggest, therefore, that even though I can measure one or the other, that they're both possible there is a thing that we don't say now, and then we can use normal logic and get away with it without falling on our face too much, okay? Or at all, in fact.
You're not allowed an and, you must have an either or.
No, we're not even allowed an either. Oh, in a certain sense, it depends. Yes, we can't. It isn't quite an either or because there are other combinations. It's a little more subtle. And I'll try to explain the subtlety in the next lectures. But I believe that we are really all here together in appreciating, and I think it's marvelous that we can understand this, that we appreciate this reastably. It's quite good. Thank you.
Okay, if you're obeying this rule,
Yes.
if you statement which says that you're now allowed to make certain statements and believe them anyway.
Right.
Okay. What does you made a statement earlier which sounded to me like you were making exactly that same statement. You said
No doubt, because I often slip.
that
As do most people.
particles don't have to be identical, but they have to have 3 states. Okay, what does it mean to say that particles have 3 states?
What I meant was that these boxes don't have to be identical. But each box has to have 3 buttons, 3 things that I can measure so I can talk about the correlations in order to be boxes that I'm interested in for this discussion here. That's all I meant. Nothing very deep at all.
In other words,
all I said is that...
has 3 states.
No, I never went to say...
States are carried
I didn't mean...
by the particles.
No, I didn't mean to say anything about particles having three states, and I doubt if I ever said that, because in fact, this is not the way we describe that, so I probably didn't say that.
I wrote it down as soon as you said it.
All right, then in that case, I was trying to get an example of a situation that we're not supposed to say. That the particle's either in this, or this condition, or whatever. And I didn't mean that. What I meant when you asked me about identical particles or identical boxes was merely this. That all I really needed for this discussion was not that this box be exactly the same as this box. It could be a triangular box or something else. And the particles that went in them might have been different, but they're correlated. And in each one, you can measure one of three things with these boxes. And they give these results that are correlated together perfectly with three different button pushings.
Well, okay.
That's what I meant.
Well,
That's
it's not-
correct anyway,
it's not
whatever.
the threeness I'm quibbling with. It's the having is what I'm quibbling with. Can we say a particle has a state?
We can say particles have states, yes, and we do say that. But in a new way, a way which I'll explain later on. In this particular example, believe it or not, this is done with a particle which has two states. So it's therefore not the kind of thing I would say, okay, that it had three states. If I did say it, I made a mistake.
No. Yeah,
I mean, I made an error, and you're right in asking. I didn't mean to say that. So it's a mistake.
And the threeness here is in fact an attribute of the experimental setup.
Yes, the threeness here was simply a particular choice. With a particle with two states, there are many different buttons that you could measure, many different things you could measure. The situation can be more complicated. And the probabilities, however, always have this horrifying aspect that they're impossible to explain by supposing this kind of a picture. And I've just taken three to make it easy for you so you don't have to deal with complicated numbers. Actually, there are other things I could have measured about this object, which would have interfered with the measurements here. It's as if I had 17 buttons and then give you a long talk about 17 buttons here, 17 buttons there. Right? The same particles, as a matter of fact, were given. I even gave exactly the same pair. But the particular machinery for making measurements is more elaborate. There are 17 things you can try. Then it would be a story that would go something like this. If you measure any one of the 17 possibilities, okay, the left by left center possibility, and you make the same left by left center measurement over here, they always agree. If, on the other hand, you measure, let's say, number 11 here, and then check 12 over there, they would agree with a probability 0.79 or whatever, okay? And that's, you know, and with number 10, there would be another number, and so forth. And that measuring 12 changes the chances of, for number 11 to such and such, with the big complicated numbers and all kinds of stuff. But it's much easier to take the three cases with the one number, 3/4, which we always come back to explain the character. The character of the phenomenon occurs again and again, that these numbers that I would have to give you for the 17 case would have this property that are inexplicable by supposing you have cards with 17 different, with red and green faces, and there are 17 cards in there and so on. Okay? But the number 3, therefore, is exactly what you said. Simply a choice made for exposition or pedagogical purposes to make the simplest possible example.
But isn't this true of all statements about states, that it's always really a statement about the preparation and setup?
I don't know what you're saying.
Not about the particle itself.
I don't know what you're saying. All I've ever said is what happened when you push buttons, or what I should have said. But since we're trying to discuss theoretical explanations of what happens when I push buttons, I may have some of the time said, let us suppose that it's in one of 3 conditions or whatever. But that was a way of thinking. Yes?
The possible the ambiguity in here was we got to have 3 states, meaning we got to have 3 things to measure, or 3.
Oh, yes, we do have to have at least 3 things to measure in order to see a paradoxical situation.
Yeah, I think that's how you use the word states in that case.
Oh, is that right? Oh.
I don't know.
Well, whatever. I'm sorry if I confused this thing.
I'm not worried about that.
Okay. Well, maybe you're worried about something you already knew before you came here. If that's the case, we're not allowed to discuss it.
I think there's something that you'll probably clarify in
Yes.
what you're going to say later on.
Go on. So yes? Well, let me get a chance at it, and then if you're still unhappy, we'll be very happy to try to explain, okay?
So what's the big deal now about Bell's theorem?
What do you mean, big deal? That we've told you the
It is a
deal.
big deal. He showed it. He showed it.
We showed you. Don't you think this is a big deal, these funny numbers?
I do think it's a big.
Okay, that's all the deal is.
That's the big deal.
That's the big deal. The Bell's theorem is a contribution to that deal, which is to point out mathematically that it has to happen. People knew it had to happen before. All he did was demonstrate it. It is not a theorem that anybody considers of any particular importance in quantum mechanics. We who use quantum mechanics have been using it all the time. Pay not much attention to it. It's not an important theorem. It's simply a statement of something that we know is true, sort of a mathematical proof of it. Once you've seen this example, you know it's true, that you can get situations that you can't explain. All of this is a demonstration mathematically from the original equations that this can happen. But you know it can happen from this particular example. So it is not really a theorem that stands in a big deal in the middle of the subject and represents a big contribution that before we had Bell's theorem, there were things that we couldn't figure out, and after we had Bell's theorem, it was a new light. Not at all. It's just a mathematical statement of something, a more precise statement of something we all knew. Okay?
People are trying to test this. Are there tests going on, as I understand?
Well, they're always trying to test whether some of these predictions of the quantum mechanics that seem paradoxical from the point of view of classical thought, or these making this assumption that a thing has to be this way or that way before you look at it, that they want to not break down that and think that maybe some of the things that are predicted by quantum mechanics are false. And so every time we take an example and discuss it, and they don't like that example, they think it can't happen, it's too crazy, then they insist that ask somebody to check it, or they try to check it. But none of these things have ever failed to work as expected. I really do believe that the quantum mechanics is fundamentally correct, and that all this is simply a psychological trouble that we have. It is extremely difficult to get used to it because it's so much common sense and common knowledge that gets this idea that when you're not looking at something, it's either this way or that way. And to be able to say that, by God, you can't even say it's either this way or that way when you don't look at it, but hey, it must be either this way or no, if you say that, you're going to get in trouble. They say that can't be so bad. There must be that nature isn't quite like that, and every hope that they have is one by one so far demolished, okay?
Well,
whether they can find a way of doing it some other way, I don't know, but that's the way it is at the present moment.
The way I understand it, some people think about Bell's theorem who philosophically they believe that the universe is somehow connected. They try to use this idea that there's this connection between these boxes, let's say, which is equivalent to Bell's theorem, to say that indeed there is an instantaneous connection between things in the universe.
Yes, well, they would like to do it that way. Yeah. I must say to you that because this is unfamiliar, that there do appear all the time when you're thinking about things, difficulties that you're not satisfied with. And I'll try to explain some of those further on when we talk. The difficulties if we try to apply this idea somehow to the whole universe or something like that. And you say, well, we're in the universe and we're pushing the button isn't something done externally, and how is it done inside when, if you can't talk about the condition that things are in, how can you talk about the condition that the universe is in? After all, we're in it. And things like that produce a certain amount of trouble which haven't been thought through very well and leave us with a very uncomfortable feeling that the story isn't finished.
could it be that by
Make copies by a certain process, which I can call, for instance, one of the processes of making copies would be, the hell with it. Don't pay much attention to what's in the other. Then all correlations are lost. What's in one box has nothing to do with the other. That's a lousy way of making copies. One of the best ways of making copies with the most amount of correlation is there is a special way, a special kind of interaction that you have to make these copies. It's a process, the printing process, whatever, which makes the copies a special way so that what happens with the left button is correlated perfectly. That I can push any one of these boxes and it'll agree, but only for the left button.
But you could make it so that...
However, there's another process by which I can make another 1,000 sets of boxes, but I have to have the interactions different. I have to know what I'm doing ahead of time. So I make the copies. The process of making the copies is different, and for that one, it's the central button, which is correlated for all the boxes. And this third way of making the copy, the correlations, could make the third one agree. And there are other ways of making the things so the correlations aren't perfect and so on, but the more perfect ones are the more interesting ones. Is that what you want? I can do one or the other or another, and I can make, we can discuss other possibilities, but I wanted to clear up this. Does that clear up this difficulty?
Could you say instead of left button, any specific button?
Yes, I could choose any specific button, but I can't choose the button after I've made the correlations. Huh? The process for correlating it depends on what button I'm aiming to correlate. Okay, I got to know that ahead of time. There's a left correlating measurement scheme.
In other words, you can't take a population where number 1 correlates and mix it with a population where number 2 correlates and then do an experiment.
I think I think it's probably been mostly cleared up, but it's looked as if you were always correlating the thing on the left side.
I was.
Or the one with number 1 or whatever.
I was.
As if maybe you can't correlate the one on the right-hand side. It would be better to kind of randomly jump around and say, well, let's say we push it.
No, well, if I randomly jump around, I see, yes, okay.
And then we've got 2 all correlated this time, and some other time randomly choose number 3.
No, just a moment. No, just a moment. Let me just say something and see whether there's a misunderstanding in reality or just in words, okay? What's possible is to make...
To find out which is which.
Well, I don't know. I have to think about that. If I mixed them up and then I tried to check which were pairs, I might be able to figure out which is which. I don't know. Yes?
Do you mean that you don't mean, like in our problem, it's not the initial button, but a specific location?
Yes, left, right, and center. We've been using that one.
So we can only choose one of those locations, but it's not the initial press that
No, no.
Because in our example before, it was the initial press, no matter which position it was.
That's correct. That's right. Yes, 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 yes. I see now what was... Good, good. Now we get the...